All right, and I think we're good. All right, so today we're going to talk about differentiability, which is essentially how we can tell when a derivative exists and when it doesn't at a point. Okay, so are there certain places on a function that we can't take a derivative? And like I mentioned earlier, we've kind of already talked about this, right? Talked about this left and right-handed derivatives, and if the left and right-handed derivatives don't match, then we end up with a spot that's non-differentiable. And that's basically the crux of the whole thing here, is determining that. But as a result of that, there are some different types of things that you could see on a graph that are like red flags right away that, oh yeah, right at this spot here, we can't do a derivative. And so I want to briefly just go over what those are, and then we'll get into more of okay, now that I have a equation, how can I work with it to figure it out that way too? So we'll start with how f prime of a might fail to exist. All right, and there are four basic ways you're going to see this. And this one should look a bit familiar. This is like a very obvious look at when the slope from one side does not match the slope from the other side. Okay? And it creates a corner in the graph. So something kind of like that. So this point right here, let's say this is at 1. So f prime of 1 doesn't exist because it's a corner there. Okay, so you guys see that? How the slope from the left is obviously negative and the slope from the right is obviously positive. They're not going to be the same, so you can't have a derivative there. So when those two slopes don't match, it always produces a corner like that. Okay. Another way, very similar to this one, is something called a cusp. And a cusp does like this. So it's instead of two lines coming together, you have two curves that come together. But still, do you see how the slopes on either one of these are not really matching? Slopes on this one are coming down negative. Slopes on this one are coming down positive. They're not going to match when they come together. So at that corner, f prime does not exist. That's a cusp. All right. Another way this might happen is if you have a vertical tangent. And this is pretty rare. We're only going to come across a few functions that actually do this. Okay, but at that point, for a function that might have like a shape like this, at that point right in the middle there, think about trying to draw a tangent line to that graph. Okay, as this thing comes up, right in the middle there, your tangent would technically be exactly vertical. And what's wrong with having a tangent line that's vertical? What's undefined about it? It's slope, right? So you can't have an undefined slope and have a derivative, right? Derivative has to have some value to it. So it doesn't work. So in this case, this would be f prime of 0. Doesn't exist. And that's because of a vertical tangent. These are probably the most difficult to identify just by looking at an equation. The corners and the cusps we'll be able to do without too much trouble, but vertical tangents kind of sneak up on us a little bit. So That's another way. And then the last one, this one might seem kind of obvious. I don't know. But this one's not so much about the left and right-hand derivatives as it is the function just isn't connected there. There's no way to make a tangent. So if you have any kind of discontinuity, so let's say like one side of the graph is coming along like this, stops, and then it picks up again over here and like keeps going or something, you can't have a derivative at that point. Okay, so like at 0 in this case, can't happen. To be differentiable, a function has to be nice and smooth and connected all the way through. If you want every point to be differentiable, it has to be nice and smooth and connected. So any kind of a discontinuity doesn't work. So in this case, f prime of 0 doesn't exist, and that's because it is not continuous. So a lot of what we're going to be doing with this is going to be taking a look at a function and determining where a function is not differentiable, and if it's not, which one of these 4 cases do we have going on? Okay, so let's investigate that for a moment. And the more you know about what graphs look like, the easier this is going to be too. Case in point on this first one. So let's take a look at f of x equals the absolute value of x minus 2 plus 3. And we want to know, where is f undifferentiable? And why? So, taking a look at the 4 different ways we can be undifferentiable, what do you suppose is going to be the one we're going to run into with this one, knowing what the shape of an absolute value looks like? Should be a corner. Yes. So let's figure out where that corner is. So the graph of x minus 2 plus 3. This is the graph of the absolute value. It's been translated. We got x minus 2, and then there's a plus 3 on the outside. So how has this thing been translated? You got it. To the right 2 and up 3. So let's sketch that graph real quick. So over 2, up 1, 2, 3. All right, there's its vertex. And it's going to do this kind of a thing from there. Okay, so where is this function non-differentiable? At x equals 2. Yep. So does that mean the entire function is non-differentiable? Can't do a derivative of this thing at all? No, not the case. It just means at exactly 2, it's non-differentiable. But you can definitely take the derivative anywhere else you want on this thing. In fact, just look at the graph and tell me, what would be the derivative when x is equal to 3? Nope. When x is 3 would be like over here. Positive 1, right? What about when x is equal to 1? Negative 1, right? So you can do derivatives other places. It's just at the corner, that's a problem. So if I said to find the derivative at x equals 2, you'd say, nope, sorry, can't do that. Got a corner. Okay? So non-differentiable at x equals 2 because of the corner. Question? Uh-huh. Remember, f prime means derivative. So f prime of 1 doesn't exist would be the same thing as saying f is non-differentiable at x equals 1. So on this one, when I say f is non-differentiable at x equals 2, I could have just as easily said f prime of 2 doesn't exist. You can do it either way. Yep. That's an important point, too. I'm okay with you guys describing this either way you want. Either saying it in words, non-differentiable at x equals whatever, or f prime of whatever doesn't exist. It's saying the same thing. Yep. So, okay. Let's take a look at some other ones. So most of these are going to end up being piecewise functions. So let's do one of those. And let's say we're going to do x squared for x less than or equal to 0. And we'll do x to the third for x greater than 0. And I want to know, does this function have a place where it's non-differentiable? And if so, where's it at? Now, if you had to take a guess at where it was non-differentiable, where do you suppose it would be? At 0. Because what you know about these two functions, does x squared have corners, cusps, discontinuities, vertical tangents, any of that kind of business? Just regular x squared? No, right? It's just a regular, smooth parabola, nothing funny going on. X to the third? Any kind of weird, funky business going on with that one? Any corners? Any cusps? Nope. Any vertical tangents? Discontinuities? No. None of that, right? So the only potential place where this could have a problem is when x equals 0, right? So that's what we're going to want to check around. And anytime you see a piecewise function put together like that, that's where your attention should go. Where do the pieces come together? Because that's where I really want to check things, to see, are the slopes meeting up the way that they should, where the two pieces come together. So we're going to do a derivative for x squared at 0, and we're going to do a derivative for x to the third at 0. Okay? So we'll start with this will be our left-sided derivative. So the limit, we have a choice. Do you want to do the h or the x definition? Do we care? Do the h? Okay. So we would do f of 0 plus h minus f of 0 over h. Okay, and from the left, we're going to use x squared. So f of 0 plus h, whoops, I got to write my limit again, would be the limit as h goes to 0 of 0 plus h squared minus f of 0, which is 0, all over h. And then cancel, cancel. We get the limit as h goes to 0 of h squared over h, which would just be h. Plug in your 0. What's the derivative got to be? 0. I kind of ran out of room, so I didn't write the last step. But you can cancel an h, plug it in, it's 0. Okay, so if this thing is differentiable at 0, we're really hoping that the right one comes out to 0 as well. So let's see what we get going from the right. So in this case, we would do the limit as h goes to 0, f of 0 plus h minus f of 0 over h. But now we're interested in the other piece, the x to the third. So for that one, limit as h goes to 0. Now we got 0 plus h to the third minus f of 0, which is 0, all over h. So we would have the limit as h goes to 0 of h to the third over h. Well, once you cancel that, what do you get?